So welcome to our very first homework assignment. This is number 1. And just to recap, in the class we learned about localization, we learned about histogram filters, and we programmed some in Python. So the homework assignment will cover this, plus some very basic probability. In the first question, I want to ask you some very basic probability questions. We have a random variable x, and the probability is 0.2. What's the probability of the complement? We have two random variables, x and y, whose probability individually is 0.2. And x and y are independent. What's the probability of the joint x comma y? And we have a variable p of x with probability 0.2. And we have two conditionals, p of y given x and p of y given not x, both 0.6. What's the probability of y? Here you have to apply total probability. The correct answer in the first case is 0.8. This is just 1 minus 0.2. If x and y are independent, then we just take the product of those two things, which is 0.04. And in the last case, it turns out x and y are independent, but just by coincidence, because the probability of y is independent of what x says, and therefore the outcome will just be 0.6. Put differently, no matter what value x assumes, whether it's x or not x, y is always 0.6 probability, so it must be that p of y is 0.6. You can actually compute this using total probability, where p of y equals p of y given x times p of x plus p of y given not x times p of not x. When you plug in the numbers, you get 0.6 times 0.2 over here, 0.6 times 0.8 over here, the complement of 0.2. And if you regroup this, so you put the 0.2 and 0.8 together into 1, you end up with 0.6. So let me ask a localization question. You remember a robot operating in a planar environment has usually 3 coordinates. It has an x coordinate, a y coordinate, and a heading direction, often called orientation. Now robots, flying robots have more coordinates. If you can orient a robot fully in free space, then you have an x, y, and z. And you also happen to have 3 rotational angles, often called roll, pitch, and yaw. So if you build a localization system for robots with higher dimensional state spaces, I wonder how the memory use will scale for our histogram-based localization method. Does memory scale linearly, quadratically, exponentially, or none of the above? In the number of state variables used in localization. So again, for a robot operating on a plane, these are typically 3 of them. So the number of state variables would be 3. If you were to look at a flying robot where you have x, y, z, roll, pitch, and yaw, you would get 6 such variables. And I wonder how the memory use of the basic histogram localization scales. Please check exactly one of those 4 boxes over here. And the answer is exponential. Suppose we resolve each variable at a granularity of 20 different values. So there's 20 different bins for x and 20 for y and 20 for theta. Then the joint table over all of those will be 20 to the n, where n is the number of state dimensions. And that's an exponential expression. And there's unfortunately no easy way around it. That's the biggest disadvantage of the grid-based localization method or the histogram method, that the scalar of memory is exponential, which means it's not applicable to even problems with 6 dimensions, because you can't really allocate memory for 6 dimensions. So I'm not going to quiz you on base rule. Say you own a house, and you know that the house might catch fire in your absence, but the probability of it catching fire, as f over here, is small. It's 0.1%, 0.01. Let's say every afternoon you talk to your neighbor, and every afternoon you ask your neighbor, does my house burn? Of course, you're a little bit paranoid if we do this, but for the sake of the argument, let's just assume we do this every afternoon. And this afternoon, he comes back and says, yes, it burns. So B, you happen to know that the neighbor is not very truthful. In fact, every time you ask him a question, you know there's a 0.1 chance, a 10% chance, the neighbor will just produce a lie. And a 0.9 chance the neighbor actually speaks the truth. So you ask him exactly one question, does my house burn? It says, yes, it burns. but you know that the probability of this being a lie is 0.1. So in applying Bayes' rule, I'd like to first compute the non-normalized posterior. P bar now stands for non-normalized, of fire given the neighbor just called, and the same for the opposite event of no fire given the neighbor just said yes it burns. And after you've done this, I'd like you to compute the normalized values that have to add up to 1. So please enter all 4 values for this homework assignment. And here are my answers. The prior for fire is 0.001 times the probability that the neighbor now correctly says yes it burns, which is 0.9. He lies with probability 0.1, so the complement is 0.9, gives us 0.0009. For the complement, the prior of no fire is 0.999, but now the neighbor would have lied, which multiplies with 0.1, which gives us 0.0999. Now these two values don't add up to 1, so the normalizer will be 1 over these two things, which is about 9.92. So multiplying these with that normalizer gives us approximately 0.0089 and 0.991. So the answer your neighbor gave you, yes it burns, raised your probability from 0.001 to 0.0089. It's still small, but it's significantly larger. In fact, it's approximately 0.9 times as large as the initial probability. And the reason why that's the case is it relates to the 0.9 of probability of speaking the truth. It's not exactly 0.9 because of normalization, but it's approximately 0.9. This is our first programming assignment. In class, we localized the robot in a 1D world with a number of grid cells, where each grid cell could have a different color. And the measurement vector was a sequence of observations. Our world was cyclic. If we fell off one end, we would continue at the other end. In this assignment, I want you to do the same for 2D worlds of arbitrary dimension. Just as before, begin with the uniform distribution, as we always do in global localization. And then we have a number of motion commands. 0, 0 is no move. 0, 1 means you move to the right. 0, -1 means move left. 1, 0 makes you move down, not up. And -1, 0 makes you move up. Again, the world shall be cyclic. If we fall off one end, like over here, we continue at the other end, like the one over here. So here's a simple example of the type code I'll give to you as a specification of the problem. And then you have to compute what my code computes, but that you can't see right now. The world in this specific instance is a 3x3 matrix, 3 rows, 3 columns. It has only 2 possible colors, green or red, and this specific world has only a single red at the center location over here. We have a motion vector and a measurement vector. We start with the motion. This one says stay in place, and this one says we're going to observe red. And additionally, I give you 2 more variables called sensor right and p move. Sensor right is the probability that your sensor measurement is correct. In this specific instance, I set it to 1.0, which means the sensor value is always correct. P move tells you at what probability the motion is executed correctly. Right now it's 1.0, it's always correct. If it's a smaller value, then the motion might fail. And when it fails, our robot won't move at all. So let's just execute this. Here we didn't move, we observed red, and we had a noise-free sensor, and as a result, we get a matrix that said 0 everywhere except it's 1 at the center location that has a red color. Let's modify the world. Let's make this grid cell over here red as well. And then now let's just rerun the code. And what we get is a matrix just like the previous one, but now we have 2 winning grid cells, both of which have a 0.5 probability, so that all the probabilities add up to 1. Let's now model a noisy sensor and set sensor right to 0.8. Your code should now compute the following: a 0.06 for almost all grid cells except the two winning ones, which come in at 0.26 and 0.26 each. So check that your code does this. Let's now bring in some motion. After not moving at all, I assume we're going to move one to the right. And we always have to have as many measurements as motions. So let me add a second measurement. Let's say we sense red again. Intuitively, this lands us at a square over here. Why? Well, we didn't move in the beginning. We saw red. There's two possibilities. But now we move again to the right side. We see red again. That makes this cell over here the most likely. So let's just check. And as predicted, almost all cells have a probability of 0.03, some of 0.13, but the one over here has a probability of 0.5333. If we set our sensor probability to 1.0, that is, there's no sensor noise, we get back this array over here, which assigns all probability to the rightmost cell. Finally, I want to show you what happens if we modify the move variable. Say our motion succeeds only with 0.5 probability, and with the remaining 0.5 we remain at the same location. This doesn't affect the first motion command, because success and failure is the same thing here, we don't move. But this one over here, there's a 50% chance of moving and a 50% chance of staying at the same location. Let's run the code. Here's our posterior probability. The cell on the right still wins, but now with a smaller total probability of just 0.46. If we now assume perfect sensors, by setting sensor right to 1.0, we get this thing over here, where a 0.66 chance is associated with the right cell over here, and a 0.33 with the possibility that we moved this specific red here twice by just not moving in between. Check your code to make sure it gives you the exact same output result. Finally, I want your code to execute input as complex as this one. This is a 4x5 world, 4 rows, 5 columns, all with the reds or greens. There's only 2 colors. There's a sequence of measurements of 5 elements and correspondingly a sequence of motions of 5 elements. All the measurements are green. The motions are don't move at all, move right, move down, and move right again. And then there are certain sensor probabilities and motion probabilities that I can set at will. I set it to 0.7 and 0.8 over here. Now if we look at the sequence green, 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 where we first don't move at all, then move right, down, right, you find that the most likely match in this world is we first sense this green over here, we then moved right to this green, we moved then down to this green, further down to this green, right to this green over here. So this would be the cell with the largest posterior probability. It is the 3rd row and the 4th column. Let's run it. And here's the result. But if you look for these probabilities, 0.011, 0.024, and so on, you'll find that indeed the largest element is the one over here, 0.3535. And it's our 1, 2, 3, our 3rd row in our 4th column that gives me this large probability. So I want your code to produce numbers just like those, and we'll check that you got the code correctly. In summary, read your colors, build a probability distribution of the same dimensions, in this case 4x5, initialize them with a uniform distribution, execute a motion first, then measurement, motion, measurement, motion, measurement, motion, measurement, and so on. You can safely assume that the measurement vector is of the same length as the motion vector. Using those measurement correctness probability and motion success probability, and then compute and output just the final distribution. If you've done this, you'll succeed. So here's my solution to the programming assignment. And it's quite straightforward given the class, but I'm really proud if you got it correct, because it enabled you to program your own localization algorithm, very similar to the way we do it at the Google self-driving car. First, I did 2 simple bookkeeping assignments. I assigned a value to sensor wrong as 1 minus the probability of sensor right, and a probability of staying, that is a motion failure, as 1 minus the probability p move. Let me scroll down very slowly. Let me first go to my main routine. I actually put a little check whether the length of the measurements vector is the same as the motions vector, and it would give me an error message if not. Of course, this wasn't necessary for you. I just did it because I want my software to look nice. Then here is my initialization of my probability table. I compute my initial uniform distribution by calculating the size of the array, the number of rows times the number of columns, and then dividing 1 over the product of those to be my initial distribution value. And this thing over here just builds up an array of the size of my colors array, but initializes it with the value of p in it. So these two lines over here give me an initial uniform distribution. And then I iterate. I go through the number of measurements, which is the same as number of motions. I move first using the move command, by which I provide my current distribution and my motions command to obtain a new distribution. And then do the same with the sensing command. I take my current distribution, the world itself, and the measurement vector to obtain a new probability distribution. When I've done this as many times as I have measurements and motions, I output the final distribution. So much for the main routine. I now have to specify what move is and what sense is. Let me start with sense. This is my sense routine. It goes from here to down here. As an input, I have a probability distribution and my world map. They're both of the same size. And a specific measurement, which is either red or green. I construct inside my new posterior distribution. I initialize this with zeros, and it's of the same size as my vector p. In the inner loop, I now iterate over all elements in my grid cell. I compute whether the measurement matches the color in the cell, in which case I call it a hit. Now my non-normalized posterior is the prior times this big sum over here. It uses sensor right if the measurement was correct, and sensor wrong if the measurement was incorrect. Finally, I add up all the values in aux. I do this with the variable s. So down here, I can normalize aux to have a total probability of 1, and then I return it. The move command takes as an input a distribution and a motion vector. It constructs the next distribution just like before as aux variable and sets it to 0. And now I go through each grid cell, and for each cell I collect possible cells that the robot might have come from. With probability p move, it actually moved, in which case its prior coordinate would have been I minus the motion command. That's because we go backwards in time. And this is the truncation indicating we have a cyclic array. And we do the same with j. Let me scroll very carefully. It's j minus the motion command, again in a cyclic fashion. But it might have been we didn't move, in which case we just use the probability of that specific cell multiplied by the probability of staying. Now this line together gives me the correct probability for the variable I and j. I don't have to normalize because it's not base rule, so I just return the corresponding posterior distribution. I also have a little routine called show that goes through the entire probability field and computed all these probability vectors of p. That makes it slightly better formatted than just printing p in a single command. So if I run my software with this specific word over here, it initializes p as 1 over 20 because there's 20 grid cells. It then runs 5 times through the motion command, the measurement command, updates those, and then shows me the final result, which I already explained, which is the array over here. If you got this correct, then you've done something quite amazing. You've programmed the core of Google's self-driving car localization methods. In Google's case, the world isn't as simple as just red and green. In Google's case, these are carefully assembled 2D surface models of the road surface. But that doesn't affect what we've programmed here. It makes the measurement function slightly more involved. The fact is that the thing we programmed here captures the key of the probabilistic inference necessary to localize the Google car. So if you program this, you just have to replace the simple matching of a measurement of green with an image matching of an entire image you record with an image in your map. I leave this as an exercise because I can't do this in this Python environment here. But I congratulate you that you really managed to do something quite amazing, which is build an amazing piece of localization software. So congratulations, you made it through homework assignment number 1. You learned about Monte Carlo robot localization with a technique that I often call histogram filters. You've implemented it successfully and you learned a lot about statistics. This all in just a single class. Congratulations, that's really awesome. Now next week, we talk about Kalman filters and tracking other cars in traffic. And we're going to implement our first Kalman filter. So I see you in the next class.